Okay, please.
Thank you very much, and thank you for coming. And I'm talking about this work with Joe Evans, and I mean, she talked about one half of the work already, so if you have been there, it might be a bit repetition. And to be honest, it's mostly questions, and we only have a very tiny result. So I still think it's really nice to talk about it, because I think it's in general a really interesting question, and since we're at a kind of kinetic semester program, hopefully we have some discussions and can find something what we can do. So it should be really interactive. I mean, so if you don't see anything, just don't see anything or would need some explanation, just stop me. Because we don't know that much about it, so we can definitely have time to slow down and explain. Okay. So we have a kinetic problem, so we can think about what's the typical linear kinetic equation. So in the kinetic equation, by the name, we're looking at the density over phase space. So it's a function of the spatial position x and v. And if we look at the evolution is typically written as dt f plus some kind of transport operator equal to some kind of collision. And the main thing I want to study is what's happening if I add a kind of a spatially dependent weight here, sigma of x. So that's the main thing we want to study. And I mean, what you can think of if it was something concrete, the easiest thing is to just take the domain, to just take the torus, the velocity, so that's the spatial domain. For the velocity, we just take the whole real numbers for possible velocities. We just have the free transport. So t is nothing as v times dx. And the collision, you can just take as a linear Boltzmann equation. So L of f is nothing else than the density of f, which I write in this final bracket, times the Maxwellian distribution constant. So that's kind of the simple setting you can have. And if you have such a simple setting, you can just compute the spectral gap. I mean, that's something you can, especially on the torus, you just take the Fourier analysis and you just compute the spectrum. So if you forget what the sigma, we say sigma just to be constant, but it's not depending on x anymore. In this case, you can just take Fourier transform and each mode separates, and we can just compute it. And what you see is that you find spectral gap for the decay to equilibrium. And I mean, here you see, I mean, this kind of decay to equilibrium is really what's this kind of really coming from the fact that I have a collision operator, which has this degeneracy because it only drives, let's say, to a local equilibrium. So at each position, it just makes the velocity space equal to the equilibrium. And the transport part then mixes all the different spaces. So that's really kind of what we always think about the cyclocoercivity. That you have this kind of combination of these two effects which determine you the spectrum. And if you really compute it, so if sigma is just constant, so just a number, and we now look here, what's the spectral effect? I'm going to start at zero here. then I see that if sigma is 0, then I just have the transport equation. And as you might know, the transport equation is just shifting things around and has no dissipation. So the spectral gap is actually 0 because there's no decay. So nothing is happening. And then if you compute it, you see that it seems to be that the spectral gap just linearly increases. So up to some kind of value. So that's what you can see. And afterwards, it's kind of decreases like a 1 over x. So that's kind of the typical thing you can understand. And you see that what you see at this picture, you can now start to understand what's limiting the rate for decay.
So this is just for that particular collision operation.
I mean, if you want to do complete explicit calculation, then you need to, of course, take this BTK, but if you evaluate this, I mean, this general picture seems to be relatively stable. I think yeah. I think, yeah, if we really on the chores, then I would say that for most operators that come up for the position, it should be because quantitatively, of course, the numbers and all these things change. Okay. So we have kind of these two regimes. So first, where the spectral gap goes linearly, and where it decays. And if you look at this first part, so in the first part, so say this is some sigma critical. So the first part where sigma is less than sigma critical. We see that, so it means that the collision is weak. And in particular, it means that it's weak compared with the transport. So the collision rate is the spectral gap is really just given by the spectral gap determined by the homogeneous equation. Because in the slow regime, the decay is really just given by the homogeneous equation. So that is dt f is equal to L. So homogeneous just means I just have to be a function of velocity in any space. So if you just have some kind of random process, you can just think that it depends on how much time you need to thermalize your velocity distribution. And the transport just makes it always is always fast enough to kind of give you then the decay for the full. But then you see that at this critical value, the effect changes. So because if I would just have this behavior, this would just be the spectral gap would be more and more increasing if I increase sigma. So there's something happening. And you have, heuristically, you can relatively easily understand what's happening. It's just basically that if you change the velocity more and more, your average velocity of a particle becomes 0. And then the transport equation doesn't move anymore. So kind of your average velocity goes to 0, and you somehow mean that the transport doesn't mix you the different particles. So you then see that you're really in a regime where essentially your velocity distribution is thermalized faster, but if you just have some kind of some space, you have mass, it just can't move straight out anymore fast. So the main question is, how is this combination acting? So so we can phrase it like this: can a spatially inhomogeneous weight sigma increase the spectral gap? So if you think about this, it's really about like, is this kind of combination of these two effects in some sense convex or not? So if you just make, so the easiest thing that is that if I have to just make this sigma to be 0 at some point, and then it's more big, small and big. Then I would have mentioned that I still have these two effects. But now, since I have these kind of parts in between, where there's no diffusion anymore, the transport, it really easily manages to spread the particles onto it. So at least for us, it was very unclear whether such a combination would be able to increase the rate. And as I mean, you have basically these kind of two different parts, and then just combine them spatially, and then it's like, do you have a convex combination or what's going to happen? Okay. There's a kind of side remark that there are physicists or kind of people who physics who look at this thing, and they suggest that it's true for time-dependent sigma. So that's a slightly different question. But there you just say, okay, I still have the space is still constant, but now I just change sigma in time, so I just have a small time where it's really strong. So basically, all the particles get a new velocity. Then I just let them move around, then just redo it. So from that respect, you might say that it's reasonable to say that it's a nice thing to do. I mean, one motivation, which I think is quite nice. Of course, you can just think of as a kinetic model, and you have some kind of physical system which you want to control, and you want to see how much you can control. That sorts of thing. But if you just want to say, a very nice application is the Hamiltonian Monte Carlo method. Monte Carlo method. And so the idea is, you want to sample from a distribution mu, which is proportional to e to the minus v, for some kind of potential v. And so this kind of what you typically have some kind of in Bayes' theorem or something like this. And how can you sample from this? One way is you just create a stochastic process which has as a stationary state this state here. So that's the thing tips can do. And the Hamiltonian is, say, take a stochastic process of of a kinetic form, so x and v, such that it converges, or the distribution converges to the Gibbs measure e to the minus vx minus v squared half. So if you take the Maxwellian velocity distribution, but I mean, you can just basically take anything. And so if you have this kind of stochastic kinetic process, which you know that it converges to equilibrium, which has this form, then I can just run this process and sample from it, and then I will find distributions of this part. And the efficiency of this algorithm really depends on the spectral gap. And what you see here is also that the big question, which I have no answer about, is how does the potential, so if I have potential V, how should this influence the sigma? How does, or rather say should, a potential V influence the sigma for fastest behavior? If you know something good about this, it'd be nice. So that's a very broad question. And what Joe talked much about, kind of the first result is that you just look at some kind of perturbation. And I mean, at least heuristically, you just say that if you have a spectral gap, or you have a spectrum, so you have just eigenvalues. And if the spectral gap is just determined by one critical eigenvalue, then you can just change the sigma, and depending on which direction you change the sigma, this eigenvalue will move. And now, if I can do this, I can always move it so that the spectral gap increases. So the heuristic really says that there needs to be a degeneracy. And that's what Joe talked a bit more last time. That in this kind of particular model, which I explain in a second, where I can actually do some things that there we can really make this fully rigorous, this perturbation, and which can give us the kind of conjecture that the sigma should somehow play well with symmetries of the system. Because if you have symmetries and you keep them, then you have already lots of degeneracy. And if you break the symmetries, then you have and typically you have this kind of singular eigenvalues, and then you can just push them around and turn the gap. Okay. So that's kind of the whole idea and what we want to do. And now it's a bit balancing that we can only do very little. So if we can't really do much in general, we just go to the simplest model we could think of. Okay, so what's the simplest model we came up? And that's what's called the so-called Goldstein-Taylor model. And that's really just BTK. So that's really just a BTK where the velocity is either plus or minus 1. So it's kind of extreme case of a discrete Boltzmann equation, and you really just have two possible processes. So in that sense, I would say it's really the simplest one you can think of. And typically it's written that U, I mean the typical notation is written ETU plus U dx is equal to sigma 1/2 V minus U and ETV minus, sorry, dxu minus dxv is equal to sigma 1/2 U minus V. So that's the technical notation. And this is really U is just the distribution of the velocity 1. So it's the distribution of velocity plus 1, and V is the distribution of velocity minus 1. So that's kind of the simplest way you can think of this. And for the space, we just take the torus, and so it's a one-dimensional torus. And now you have a choice: either you take the length 1, and then kind of the first eigenvalue you need to scale to 2 pi, or you take the length 2 pi, but then you have a length of 2 pi, and you need to think about this. So we just set its length of 2 pi, which is a bit annoying because either values at some point you have flying with factors of 2 pi around. Okay. And now in this really simple setting, we can prove our kind of second proposition. So the first one is really about this perturbation argument, which I kind of skipped because it's what Joe talked about. But the second one is really the proposition that the fastest decay rate is obtained with constant sigma equal to 0. And this is really a global statement where you really claim that over all possible sigma, it's really the fastest decay rate. And that's, I was quite, I think it's quite a nice proof. And sadly, it really uses this simple structure. So it's cute, but maybe not so generally useful. And the key point is that actually you can think of this as a wave equation, or you can rewrite the equation. So now for the rest of the talk, I want to talk about this proof of this. And the idea is that you rewrite this equation. So we look at rho, which is just U plus V half, or we take square root of 2, and J is U minus V for the square root. So I mean the square root of 2 is just to make sure that the 2 norms is staying constant. I mean, it's the same. And if you now look at the evolution, you see that ET rho is just following the flux from this dxj. And now the magic happening is that in general, if you want to compute ETJ, you need to know the second moment of the dx of the second moment. But because we only have 2 velocities, the second moment is equal to the first moment. So things really become really nice. We really have that this is just equal to dx rho. And then of course we have the damping term. And in this case, this damping term is just minus sigma x. So as you see, this we just, in this case, it's really like a classical wave equation. And to be fair, I mean, a similar setting question was asked where they couldn't really give such a nice answer on this level of the wave equation by Cox and John. Already quite a lot time ago. But they really came from this motivation of understanding the wave equation. Okay. So that's the first thing we can do. And so what they did, I mean, they had some kind of fixed boundary conditions, and there they did something somewhat similar. But it didn't really give them a conclusive answer. But in our case with boundary conditions, we can actually prove this really nice result, I would say, by looking at the associated Hamiltonian. Okay. So the first thing is that here, as in a pair of equation, but if I now really just want to look at eigenvalues, this dt really is just replaced by lambda with this frequency lambda. Now I have just an equation of dx, and that's really just this really simple equation that minus dx squared j plus lambda times lambda plus sigma of j. So there's nothing really happening. And now just back to the question. I mean, this is just the eigenvalue equation for our equation. So if for certain lambda I have a non-trivial solution for this equation, then I have this is my eigenvalue. And since I'm interested in the spectral gap, I'm trying to see for which lambdas I will have a solution for this equation. I mean, this maybe just a slight remark is that here I just really look at the eigenvalues, and you could say, okay, I just look at the spectral gap, and after it's not necessarily the decay rate, but in this setting it's really always the same. So you really can think of this basic matrix picture that you really just need to look at the spectrum of the discrete spectrum of your operate. Okay. So that's what we do. And what we notice is that if we have lambda as a real number, then we associate an Hamiltonian H sigma lambda to this equation. And this H sigma lambda is just the operator H sigma lambda acting on function J is nothing else than what I have here for. So now I've not really done anything, but the nice thing what I can now say is that lambda is an eigenvalue for our Goldstein-Taylor model. And this is really equivalent to saying that H sigma lambda has an eigenvalue 0. I mean, that's just the definition. But now it allows me to really study this the eigenvalues of this self-adjoint operator. And that's really the key is that this is really just a set. So this H sigma lambda is a self-withdrawing operator. And we have kind of a spectral decomposition, just basically because the inverse is compact, and then you just use your regular function analysis. So we have a sequence, an increasing sequence of real eigenvalues. So and this mu n, they just go to infinity if you take n. Okay. And the nice thing is, if you look at perturbation theory, is to say that if I change my lambda, these mu change continuously. So that's kind of the first part, that this change continuously with respect to sigma. And the kind of a classical source of these kind of stuff is the Smith-Macron. So that's the first part. And now I want to use this idea to see that I can always find this proposition that this constant sigma gives the fastest decay rate. So what I need to do is that if you give me some odd sigma, I need to give a bound on the spectral gap. And by this argument, I just really give amounts to studies when you have zero eigenvalues of this H sigma. Okay. And now we get us thinking what's happening if lambda is equal to 0. So if lambda is equal to 0, this term, so this H sigma lambda is just minus dx squared. And that's just the Laplacian of the torus. And for this one, we could just know the eigenvalue. So the first one is just 0, and the second one is just 1, and they're just kind of integers. Okay. And now I see here I'm at 0, and I just want to study when it's actually going to be 0. So it's kind of already a critical case. So I just need to know what's happening in the neighborhood. So the first part is that you just look at what's happening if lambda is really small. So you look at this case, and what I see is that now the eigenvalues will be changing, and the key information I can find is just by just using some kind of simple perturbation. This first eigenvalue is going to be negative. Okay. So that's the first good part. And what we basically do now is, if you take this picture of lambda, so we look at, just make here the notation is, look at functions e to the lambda t. So the spectral gap is how negative this thing is. So that's why I write minus just the notation. Okay. And now if I look at this spectrum of this H sigma lambda, and this, if for lambda equals 0, I see that I have this 1 at 0 and this 1 at 1. And by this first simple perturbation argument, I see that this first one will go to 0, and the second one will just stay. And this one is really just corresponding to the state that the stationary state is the stationary state. So the terminal state is just stationary. Okay. And the idea what we're not doing now is we'll show that if we're at the later stage here, back here, that there at least needs to be two eigenvalues which are non-positive. And if it's non-positive, it means that at least this one at some point needs to have crossed this part here, or just needs to be crossing this part. So that's the idea of the proof, that we want to prove that at some later point, we can choose here, that at least H sigma lambda has two non-positive eigenvalues, and then by the continuity there needs to be crossing. That means that before this value, at least at this value, for this value of sigma, there needs to be eigenvalue for our Bertrand-Taylor model, which gives us the kind of difficult side of our bound for this technical. And luckily, this is relatively possible. So we just consider two functions. So we really need to show that now we have we don't have just not one non-positive eigenvalue, but we need two. So we need two independent test functions to see that we really have at least two negative eigenvalues. So we consider these two functions, j1 of x, which is just equal to 1, and j2 of x, which is sine x to x minus 1, where phi is a parameter we can choose. And now I just have these two functions, and I just compute what's the inner product of j1 with h of times j1. Okay. So I can just compute this, and for this j1, this is, I mean, I can just give it the value, but this is negative in the regions we are interested in, and the region we are interested in is really just like sigma 1 is bigger than pi times lambda. So we see that the first one is relatively easy, and for the region we're interested in, it's negative as we expect. And for the J2, we just basically do the same argument. We compute this part. And now we remember that we still have this one parameter left. And we need to compute, if you look at this operator J2, you need to multiply it with this function sigma. And to simplify this calculation, or make this calculation work, we choose this parameter phi such that the northern term in this computation goes away. And this is just a condition that integral over this torus of sigma times x times cosine of 2x minus bx is equal to 0. So this is just to make sure that the annoying term just goes away. So it's just sort of trigonometry. And if you do this, you just compute things. This part is really kind of the critical part, so I'll just give you the expression in times. So this I just can find now. This is the L1 norm of sigma. And now I can just ask that when is this going to be 0? And this is going to be 0 if lambda is some critical value lambda sigma, which will be this value which I draw out here. And this lambda sigma is, I mean, in this case, I can just give you an explicit expression. So in this range, I know that I can bound the spectral gap in terms of the L1 sigma. And now this is, luckily, it's basically finishing all this argument. Because I can just remember the previous picture I've drawn you. I can just compare this result to the case of the stationary case. So we just use the stationary case, we can compute explicitly. So with sigma equal to constant. And as I said, I mean, there you really can compute the spectral gap explicitly. And there we exactly identify that we also found this critical value, say 2. And we saw that we had this linear growth, and then we had this decay. And this decay we find here is exactly matching this decay here. So in this sense, we really captured sharply how much, how fast the transport can thermalize the state. So we have a good spectral bound on the right-hand side. And on the left-hand side, we can just compare it with the homogeneous equation. And for this part, it's easy to see the spectral gap. And so we see that it can never be bigger than at this critical value. And with this part, we can globally prove that it's the fastest decay rate. And at this time, thank you very much, and stop it.
Okay, thank you. Questions? I'll start by asking, how do you get the 2 for the constants? Like, is that explicitly computable?
Yeah, I mean, this is really just, if you just take for the constant sigma case, it's just a bit of how you normalize your equation, then just really just computed by the Fourier analysis, and then you just manufacture by.
Oh, because this is for the discrete velocity case.
Yeah.
And if you have the continuous one, like the sigma c, the highest point, even for constant ones, can you get that?
I mean, I have the feeling that yes, I mean, typically then you just decompose it in kind of Fourier in space or something like Hamid polynomials in velocity, and then they decouple typically. You normally should be okay.
Okay. Sure.
When you introduced the rho and the j, it looked to me like the rho was an average of the 2 velocities, and the j was sort of the first moment of the 2. Is that intuition, do you think, like something that could be used for the like a more complicated ultimate equations?
Yeah, I mean, that's what I'm trying to say. Is, I mean, as you said, you said to me this rho, you just take a very general equation. It's just the spatial density. And then the j is just v times f. Okay. And now what we want to do is we want to compute dt of j. And in general, you know that this is dx of v squared. I mean, you use some kind of vector notation. So if you have a general Boltzmann equation, you have somehow kind of a second moment, or say J2 or something. There I'm going to call it. So then it's not closing again.
Yeah.
But I mean, it is very simple case of this Taylor model. This is actually going to be the end goal. That seems to be some of the magic of this simple model.
Between the two velocities, very simple model, when you send sigma to infinity, I'm not sure I understand what happens. You have u equal v.
I mean, sigma is the yeah.
You have sigma over 2 times u minus v and sigma to, so asymptotically, when it goes to infinity, you have u equals v. But what happens then to, I'm not sure. See what happens then for the equation. And to relate them to.
I mean, I guess the easiest,
At least
for me, is you just think of this classic process. So just for constant sigma, it means that you start, say, position plus velocity plus 1, and if you would have constant sigma, you would be moving by the transport, and you have an exponentially clock winning after some kind of time, small r1, the exponentially clock rings, and you sample arbitrary new velocity. And then the transport moves along, and you sample the second time the exponential clock. And after this time, you sample again. So I mean, it could be the same velocities. And then maybe then you always get up to kind of plus 1 velocity. So that's kind of the idea of what stochastic process doing. And now the point is that what does it mean if sigma is becoming really, really large? It means that you sample this in very, very short amounts of time. And then you just see, okay, if I just sample very, very short amount of times, then how far does your particle move? And because the expected value is 0, it basically doesn't move at all. So that's why the spectral gap decays and sigma comes down.
When you asymptotically, when you equalize the v, you have just wave equation.
Yeah, you get this wave equation, yes.
And things move in the wave equation. So it's why I'm not understanding. You do the wave equation with spin 1, and so everything is just scattered, and since it's a torus, it comes back, but it's what I am confused about. Or maybe because the density becomes constant. There's something I can't understand.
I mean, Thomas, I've mostly thought about this in this kinetics thing first, scientifically. But I mean, if you look at this wave equation, if sigma becomes large, it means that this J should be relatively small, and this rho should just be like a sum. It's small, limiting the weight. Yeah, I mean, I guess then you have the problem that you have this equation dt rho plus dxj equal to 0. So rho basically stays constant, and dxj is small because j is small. So it's dpj. That's why the equation dx rho minus equal to minus sigma of j. So now if you look at this equation, if sigma becomes really large, this means that j is basically 0. And then you see that dx of j should be small as well, so that dt rho is basically constant. So that kind of small decay.
Any other questions? I don't see any questions online as well. So in this case, let's thank Helge again for a nice talk. This one, what is this consistent with the thing from this one? If I look at it, it's not.
I mean, the terms has length 2 pi. So this is and this just
Yes, but like so in one of the equations, forcing is v minus u, and then in the other equation it was u minus v.
Yeah, but if we equalize it, then both are true. We will see
Then to balance it,
and then you can just like transform the equation, transform the relative. So yes. Also make the calculation with distance to have a flat with displacement, then with equation.
Then it's like 1 over sigma.
Yeah.
Suppose that this is going to be a constant. You have a non-constant function. And
I mean, the idea is okay. If I go back to this picture, and I say that there would be a sigma which would be give me a faster decay rate. Then I just look at this picture and see whether I'm above or below this kind of critical value for the constant. If I'm below the critical value, I know that comparing to the homogeneous equation, the decay rate is limited by this.
even if sigma is dependent on x.
Yeah.
If sigma of x is below 2, then you will get, sorry, sigma s and yes, sigma s is 2.
Yeah, I mean, you can just compare it with, I mean, you can just look at, you can just integrate over, yeah, it's a bit more difficult, but you basically intuitively just compare it with the homogeneous case and see it's okay. And then if it's bigger, then so you compare, look at the sigma of the L1 norm, and if it's bigger, you use this result, and you see that your spectral gap can be at most this curve.
So in any case, like sigma equal to the constant, 2, you get the maximum.
Yeah.
It's interesting. Thank you.
Yeah.